So, hello guys. I am Costa. I am the founder of Netdata. AI. Everyone is talking about AI these days, no? I am a little bit practical. I am an engineer, so I will be a little bit practical with this. The first thing is, how many people know Netdata here? Do you use Netdata? Oh, okay, great. In 2019, Google did an experiment. They asked Google SREs and DevOps to come up with ideas of what AI and machine learning could do in observability. So they gathered all these ideas and they started implementing them. And guess what happened? Nothing worked. Not even a single idea. So Todd did this presentation back in 2000 where he said, all our ML ideas are bad. Why is that? Why machine learning in observability is hard? So the typical process is that you go in a lab, you put some data into a machine learning model, train a machine learning engine, trains the model, and predict some outcomes. If something is wrong, you train it again. You give it new data, it makes it wrong, you train it again, and this is a loop. The main problem here is feedback. So machine learning expects you to give it feedback that this is good and this is bad, that this issue should be detected. So the problem with observability is that you never know what can go wrong. Unless you see it, you never know. So the first thing is that we need unsupervised machine learning in observability. The second is the sharing of the models. So people believe that, okay, I have database servers, I am going to train some models for these database servers, or on one database server, and I'm going to share the model to another. Guess what? This doesn't work. Why it does not work? Because even if you have two identical servers, so same hardware, same software, same dataset, same everything, the problem is the workload. So the workload that is offered to each server determines what the model will do. So the model learns actually the workload of the application. So sharing is not possible for most of the cases. There are some cases that it is. So what machine learning can really do for us? How we can use it in observability? So machine learning is the simplest way to learn the patterns of our metrics. Learn the patterns, how they behave over time. It's easy because it's just an algorithm, you push the data to it, it learns how they behave. Then what it can do is that it can tell us if a sample we just collected is an outlier or not. Does it match the pattern or not? So this anomaly detection is just a bit, either true or false. Either it is an outlier or it's not. But if you look the metrics over time, each metric over time, you have an anomaly rate. So for the past hour, this metric is 10% anomalous. Okay? Now, unsupervised machine learning like this unsupervised, no feedback. You just push the data, it starts detecting outliers based on the patterns it learned. That's it. The problem with this is that it is noisy. So it has some false positives in there. Why it has some false positives? The first problem is that some metrics are easy to model. Workload of a web server, of a database server. That's easy. But if you go to CPU interrupts, what to model? These things are like squared things all the time. It's totally random what the hardware is doing. So actually, for some metrics, this is easy and doable. For other metrics, no go. How we designed machine learning in the data? These are the objectives we set. We first said, okay, we want this to be totally unsupervised and as reliable as possible. We want this to be real time. So Netdata is real time everywhere. I don't know, for the guys that know Netdata, you know that Netdata collects data every second, and many of them. So the idea is that we want it real time. So in the flow, in the pipeline that we process metrics, anomaly detection should be always there for all metrics. It should be lightweight. The data runs at the edge. So everything we do is at the edge inside your production system. So we wanted this to be extremely lightweight. The next thing is that we wanted the anomaly information to be stored in the database. This is to allow us query for past anomalies. How the anomalies were yesterday, a week ago. And we wanted this to be integrated everywhere. The key decision here that we made is that we consider Anomaly an advisor. It's not something that it should wake us up at 3 a.m. It's something that we should use, consult, to actually do root cause analysis, understand what is interesting now or at a given time frame, or find correlations in metrics that are otherwise totally uncorrelated. We needed a rolling model. A rolling model because we needed the machine learning to forget. So you have an anomaly. It's unsupervised. You have an anomaly today. After how much time the same anomaly will be detected again? Because it will learn it. So it needs the right to forget after some time. So what we did there is that we train every 3 hours a model with 6 hours of data for each metric. 1,000 metrics, 18,000 models. 10,000 metrics, 180,000 models. So it trains a model every 3 hours with 6 hours of data. It keeps 18 of them. When a new one comes in, the last one is thrown away. What we also did to reduce the noise is that all 18 machine learning models per metric need to agree that something is an outlier in order for us to consider it an anomaly. This is the metrics processing pipeline in Netdata. As you see, data are coming from here. So it discovers, collects the metrics, etc. It passes through anomaly detection and then it is stored. And when it is stored, then we learn. So this is a loop. This is a continuous loop where we train models and we detect anomalies all the time in real time. How we made it lightweight? The first thing is that we observe that a lot of metrics are just zeros. These are errors, hardware errors, or exceptions that never happen. These things that are always zeros are very easy. We don't need machine learning for them. You just have an alert on them. If they are not zero, raise an alert. That's it. You don't need anything else. There are other metrics that are not zero, but are almost always constant. So the number they check never changes. The maximum connection pool of a database server. Unless you restart and configure the server, it will never change. So we excluded all these that are constant over time. And then what we did is that we did a sliced training. So mainly because Netdata is a decentralized system, so we sliced observability in little pieces, and each server does only its own part. This allowed us to actually train at the edge at a very small overhead. Because even if you have 2,000 metrics per server that need training, the speed of this, as you see, is 2 CPU cores per million of metrics. So 500,000 metrics training, 500,000 metrics per core. If you have 2,000, you understand that this is a tiny thing, 0 point something of a single core. Now, the key thing of storing the data in the database is to query the past. And this is the beauty of this solution, is that you, at any given time, so you have any time frame that you are interested. A weekend ago, a month ago, it doesn't matter. You can review what the anomalies were at that time. It doesn't matter what the models say today. What it matters is what they said back then. This also enabled a lot of interesting views that we're going to see in a while to actually do root cause analysis. What kind of anomalies it can detect? This is a small subset, but it will give you an idea. The first thing is that if you have a model that goes like this, you detect the outliers, the extremes, the extreme values. This is easy to model even without machine learning, but machine learning does it by itself either way. The second is that since it learns a pattern and there is something periodic happening all the time, suddenly it misses one. This can be a cap in a web server request that somehow appeared. This may be a backup job that didn't run. This may be a regular job or a cron job or something that changes something in the database that didn't run. This is very interesting. This is, for example, you have your network, nothing has changed, and suddenly you have retransmits. A lot of TCP retransmits, something happened on the network. The effect on your web service and your database servers is that you will see a small dive. Not a big one, a small dive. And then when the network problem is solved, it comes up again. This is capable of detecting this. A change in trend. So something changes constantly in trend. This is very interesting because this way it can detect memory leaks, it can detect attacks, it can detect response times that are gradually increasing all the time. And of course, sudden changes in the behavior of metrics. Like you did a deployment, suddenly half the workload is processed. It can detect even this case. I said this is a small set. It's machine learning, so it's a lot of things that does behind the scenes. It's not just only these cases. So we didn't model these cases. These are observations of what it actually detects. How is this integrated everywhere? This is a chart. This is a data chart. It looks like any chart, but pay some attention. What we added is the needle framework. The needle framework is there at the top. It says nodes, applications, instances, dimensions, and labels. The whole idea of the entire bar that we added there is first to understand where the data are coming from. What data do I see? It's just a chart, a few lines there. Yes, but what data are there? From where? That's the first thing. The second is to get an idea of what anomalies are in this thing. And the third is to pivot the data, to slice the chart the way you want. So it's a cube. You want to see it like how you want to see it. Let's see what this do. So I clicked on nodes. It says 7 nodes. It gives you a list of the nodes. It gives you, of course, how many instances, applications in this case, and metrics are there. The volume contribution of each node in the chart. So you see how much the chart will lose if you remove a node from it. The anomaly rate per node, and of course, minimum, average, maximum values, and alerts if they are there. This is for applications. Now it's the same information, but at this time is the specific application that is interesting. Again, you have anomaly rate information. And this is even per label. So each label that exists in the chart, that contributes data to this chart, is again scored for volume and anomaly rate. Now, this allows you to quickly spot, I didn't tell you, that is very important, that, come on, here is the anomaly ribbon, this thing. There is a ribbon across the chart, this purple thing, that shows you the anomaly rate across time for the entire chart. And then you have also the ability to see the anomaly rate per point. So you hover on the chart and you can see that point, that dimension on that point, what's its anomaly rate. Another thing that we did, and this is about the root cause analysis, is that we implemented a scoring engine. What is a scoring engine? All of us know query engines. They do queries from the time series data and return back some aggregations. What's a scoring engine? A scoring engine goes through all the metrics, all of them, for the given time frame and scores them according to an algorithm. What an algorithm can be? Anomaly rate. Give me the anomaly rate during that time for each metric. Give me similarity. I am looking something that looks like this. Have a big spike or a big dive there. I am looking for a rate of change. So compare these durations for every metric and give me a score of how much it changed before and after. What this does is at the end, it gives you an ordered list. So it goes through all of them. It may be millions. It goes through all of them, scores them, and gives you a sorted list of this is the biggest score, this is the second, this is the third, this is the fourth, etc., etc. Now, how we use this? The first thing, this is a data dashboard. This is the main menu where sections appear, etc. The entire metrics and the data visualizes everything by default. You don't need to create dashboards. So the idea here is, okay, you have this time frame. You know that something is wrong. You have a problem. What you do is that you click this AR button there, this AR button at the top, you click it, And the data calls the scoring engine for everything, and it gives you a score next to every section. So you can know immediately what the machine learning thinks of. It's interesting in here, in this time frame. The second is the following. When we saw anomalies happening in production systems, we realized that anomalies happen in clusters. So it's not just one anomaly on one metric. Usually, a lot of things change, get anomalous together, really a lot. And especially because Netdata collects thousands and thousands of metrics on each server, it was easy to spot it, right? To see that, come on, the moment that this got anomalous, the other got anomalous, the other got anomalous, the other got anomalous concurrently. So this allowed us to calculate a host anomaly rate. This is very simple. It's the percentage of metrics on a server that are anomalous at the same time. Right? So if it has 2,000 metrics, what percentage of these 2,000 metrics are anomalous concurrently? Then what we did when we visualized this is the first chart, this one. Every line here is a server. And then we realized that even across servers, anomalies happen in clusters. So one server got anomalous, after some time, some other servers got anomalous. In this case, all the servers got anomalous at the same time. Huh? What we did now is the following. Netdata allows you to highlight any spike, anything on this chart. You press a button, and it gives you a sorted list of all the metrics across all the servers, a sorted list, so the most anomalous at the top, that have been influenced or may be influencing this anomaly. This means that your aha moment, how we troubleshoot usually. You go have a problem, and you go and say, okay, what if is the network? Let's validate, verify if it is the network or not. Oh, no, it's not the network. Let's verify if it is the database or not. You speculate, you assume, and then you validate or you drop your assumptions. What we did here is that we flipped it. So you don't need to guess anymore. You go there, you highlight the area, you press a button, your aha moment should be within the first 30, 40 items that Netdata presents. What's the highlights? In Netdata, machine learning exists and is across the board for everything. It is totally unsupervised. It doesn't need any feedback from you. It works for all metrics, all charts, all dashboards. It's just across the board everywhere. It's available on all charts again, so you can work with anomaly rate everywhere. We have root cause analysis embedded into the tool based on anomaly, and this is made because we added a scoring engine. Okay? Now, just a couple of words about Netdata. Netdata is an open source project. Today it has more than 70,000 GitHub stars. Netdata leads the observability category in CNCF. We are not incubated by CNCF. CNCF does not endorse Netdata. But still, we are leading. We are number one in the observability category in CNCF. Next is Elasticsearch, then is Grafana, Prometheus, etc. Netdata has 1.5 million downloads every day. Right? Only Docker Hub is counting so far 650 million Docker Hub pulls. So it's a popular project. I have more time, but I have slides that, let me also say this. This is what makes Netdata unique. This is why we built Netdata. We want an observability system that is easy, that is real-time. Right? Easy why? I think that the world is making observability artificially difficult. Observability should be simpler. It is simpler. The moment that we learn to work with observability is, to my taste at least, it's extremely complicated, complex, unreasonably complex. With Netdata, we try to simplify observability. This is why Netdata collects all the metrics it finds by itself. You don't need to configure it. Of course, if a password is missing to connect to a database server and collect metrics, it will ask the password. But if it can find whatever it can find there, it will not ask. It will just collect. It will create dashboards for everything. Every single metric is visualized. You never end up in a situation that you have a metric that, where is the chart? There is no chart. Never. The next is that we have as you saw, machine learning and artificial intelligence everywhere to consult you, to give you better insights. And mainly because of the design, the data is a distributed design. So the traditional pipeline of, since I have time, I will go to show you this. The traditional pipeline of most systems is like this. So you have your servers, your infrastructure, you push all the data to some central database, and then you have dashboards and alerts. The problem with this is this thing. When you centralize everything, then you have to cherry pick information. You have to be very careful what you centralize, what this means, and then you have to put a lot of logic here on how to visualize it, how to create an alert for it, etc. So what we do in the data is this. So we distribute the code. You put Netdata everywhere, and you're done. How do I get aggregated views? You can get aggregated views with this. We call it Netdata Cloud. So this is a thin layer, a proxy that actually gets a request from you and distributes it to your Netdata servers. It collects the data back, aggregates the responses, gives them to you. Of course, you have also the ability to have parents, Netdata parents. This means that data are now copied from this cluster to this server, and on this server, you have fully aggregated views on-prem. All the data are there. So with the data, we tried to change how observability works in order to simplify it mainly, to make it easier for everyone. And at the same time, it's a monitoring system that is shipped with a lot of information. So out of the box, the data has about 400 pre-configured alerts. You install it and 400 alerts are there. That's it.